Good morning children, and welcome back to your chemistry class. Today in this P block elements we are going to do the boric acid and potash alum. These two are the compounds from your 13 group. Okay. So boric acid, which is also called as orthoboric acid, and the formula is H3BO3. So let us begin with the preparation of this boric acid. So this boric acid, it can be firstly prepared by acidifying an aqueous solution of borax. Okay. So first method, what did I say? By acidifying an aqueous solution of borax. Okay, so borax is what? Na2B4O7, right? To which we have to add acidified aqueous solution. Okay, so that would be 2HCl plus 5H2O. Clear? This is going to give us 2NaCl plus your boric acid or orthoboric acid, that is 4 parts of H3BO3, right? This boric acid, it can also be prepared by the hydrolysis of boron compounds. Okay, so by hydrolysis of boron compounds. So let us take one boron compound like boron chloride. Okay, trichloride or boron chloride. When it is treated with water, that is, we are doing hydrolysis. Okay, so we get what? Orthoboric or boric acid, that is H3BO3 plus 3HCl. We can also take boron nitride and treat it with water, and then also we get H3BO3, that is your boric acid, plus NH3, the ammonia gas will be formed. I hope this is very clear. So preparation is clear to you. Now let us talk about their properties. Okay, so this boric acid, it is a white crystalline solid. First point, it's a white crystalline solid, and it has a needle shaped structure First point is clear. Second point about it, it is sparingly soluble in cold water, or we may say sparingly soluble at room temperature, but it is highly soluble in hot water. Alright, sparingly soluble in cold water, but highly soluble in hot water. Third point about it, let us talk about its acidic nature. Okay, so what do we know about its acidic nature over here? So it is a weak monobasic acid. Okay, it is a weak monobasic acid. This is the first point. Now this boric acid is not a proton donor, correct? It accepts pair of electrons from water, or you may say it accepts the hydroxyl ion and acts as a Lewis acid. So we can see the reaction. Whole thrice, it combines, it will accept the hydroxyl ion of this water, and it is going to act as a Lewis acid. So BOH4 minus plus hydronium ion. So since only one hydronium ion is given out, it is a monobasic acid. Then next point, let us see how it behaves. Let us see on heating what does it give. So on heating above 370 boric acid, it gives metaboric acid, right? So let's see this. Boric acid above 370 Kelvin. What did I say? It is going to give metaboric acid, that is HBO2 plus water. This is called as metaboric acid. Here, this metaboric acid, let me write down over here. Further, when it is heated up till say 410 Kelvin, then it is going to form tetraboric acid, that is H2B4O7. And further, when still heated till red hot, right, then it forms boron trioxide, that is 2 parts of B2O3 plus H2O. This is called as boron trioxide. So I hope the properties are very clear to you. Now let us understand some uses. I'll write down uses in short over here so that the complete points about boric acid is clear to us. So over here, this boric acid, it is used as a preservative for the milk and other food articles. Okay, used as preservative for milk and food articles. This is one use of it. Another use, it is used for the manufacture of enamels and glazes for the pottery. Also, it is used in the solution as an eye wash. Okay, used as a solution in eye wash. And what was the other one that I said? Manufacture of enamels. Manufacture of enamels and glazes for the pottery. So this was all about your boric acid. We studied about the preparation of boric acid. How do we prepare boric acid? What are the different properties of it? And what are the uses? Now I am going to explain you even the structure of this boric acid. So this is the structure of boric acid. It shows a trigonal planar structure, okay, of BO3 3 minus units, right? They are joined by hydrogen bonds to give a layered structure, right? So wherever you are going to see the dotted lines, they represent the hydrogen bond. Okay, so let us understand what are alums. You already know that alums, they are double salts. Double salts of what type? They are of this type, M2SO4 dot M2 dash SO4 whole thrice 24 H2O, right? Over here, your M, this M, it is a monovalent metal, right? Monovalent metal, like for example, it could be a sodium metal ion, or it could be a potassium metal ion or ammonium ion. Clear? Whereas this M dash, this is your trivalent metal ion. For example, it could be aluminium ion, or it could be ferric ion, or it could be chromium ion, and so on. So this is how we are going to form certain formulas of alums. So mostly, for examples, the alums that we know, they are like potash alum, isn't it? Then we have sodium alum, and we also have chrome alum. So let us understand the formula. As I have already written the general formula, let us find out. Potash alum. Potash, already you know, it is potassium and it is also your monovalent metal ion. So your first part of the salt will be what? K2SO4 dot. The alum will be, let's say, aluminium. So it will be aluminium Al2SO4 whole thrice 24H2O. So this is the formula of potash alum. Let us find out the formula of sodium alum. Now sodium is also monovalent. So we write here Na2SO4 dot Al2SO4 whole thrice dot 24H2O. So this is the formula of sodium alum. Now chrome alum. Chrome is your trivalent. So trivalent will be your M dash, right? So the formula for chrome alum could be K2SO4 dot Cr2SO4 whole thrice dot 24H2O. Clear? So these are some of the examples of your alums. I hope this much is very clear. Now what we have to study is the potash alum, right? So let me write down over here. Potash alum is in your syllabus, and the formula, again I repeat, K2SO4 dot Al2SO4 whole thrice dot 24H2O, right? So how do we prepare this potash alum, right? So equimolecular quantities of potassium sulfate and aluminium sulfate, they are dissolved in hot water, and this solution is then cooled. We get the crystals of this potash alum, right? So let's see this. So what did I say? The equimolecular quantities of K2SO4 and Al2SO4 whole thrice, they are added to hot water and then they are cooled, and we get the crystals of what? This potash alum, that is K2SO4 dot Al2SO4 whole thrice dot 24H2O. Clear? Now we just have to know some uses of this potash alum. Firstly, it is used for the purification of water. Purification of water. Then it is also used as a mordant in dyeing. Mordant in dyeing purpose. Then it is also used for blood clotting, right? Suppose there is lot of bleeding, then people apply potash alum over it. It prevents the extra bleeding. Then it is also used for tanning leather. Then it is also used for sizing the papers, sizing of the papers, and so on, right? So these are some of the uses of alums. I hope this much is very clear. Now little more about the uses of aluminium also we have to do over here, right? So aluminium, it is used for making transmission cables, and they are also used for winding the moving coils of the motor. So I'll write down over here, for making transmission cables, for winding moving coils, right, of motor. Then where else they are used? They are used in making household utensils. Nowadays you must have seen aluminium doors are being made, the cans, the picture frames are also of aluminium, isn't it? So they are also used for making utensils, doors, windows, picture frames, etc. Then even in the packaging material, they are used for packing of the medicines, your toffees and all that, isn't it? So used as foil in packaging material. Then also it is used in the alloys, used in making alloys. If you remember duralumin, it is used for constructing the aircraft body, isn't it? So all that is also there. And last but not the least, it is the anhydrous aluminium chloride, right? Anhydrous aluminium chloride, it acts as a catalyst in the Friedel-Crafts reaction, okay? Acts as a catalyst, I'll write over here, in Friedel-Crafts reactions, right? So this was also about your alums, the preparation we did, the uses we did over here, the uses of aluminium also we did. So with this we finish off with the 13 group elements and their compounds, right? Now I shall begin talking about group 14 elements, that is the carbon family. So let us now begin with group 14 elements. Group 14 elements are also called as carbon family. Why? Because carbon is the first element of group 14. Clear? Other members of this family are what? Silicon, germanium, tin and lead. Fine. These are the 5 elements that we find in the carbon family. 1, 2, 3, 4 and 5. Now all the elements of the carbon family, they have 4 electrons in the outermost shell, and all these elements, they have ns2np2 configuration. Clear? So now let us begin about talking about the physical properties of carbon family. So before understanding the physical properties, first let us configure all the members of this family, and then we shall proceed with it. So talking about carbon, so over here the inner core noble gas will be helium. Why so? Helium means 2 electrons, then 2s2, 2p2. Okay, so this is the configuration for carbon. Now let's talk about silicon, which is the noble gas for silicon. The inner core is the neon gas. Neon means 10, then 12 and 14. 3s2, 3p2. Okay. Now let's talk about germanium. For germanium we have argon. Argon means already 18, right? Then it will first enter the D block. So that is 18 plus 10, 28, 4s2, 4p2. Okay, 28, 29, 30 and 32. What about tin? For tin it is krypton. Krypton means 36. Now this krypton after, this tin after krypton, it is going to enter the D block, that is the 4d10, right? 5s2, 5p2. Now let's talk about lead. 82 is the atomic number. So over here, xenon is the noble gas configuration with 54 atomic number. then it is going to first enter the F orbital, that is 4F14, then 5D10, then 6S2, 6P2. So this is the configuration for lead, right? So I hope this is very clear to all of you, how to do the configuration of the respective elements. Now we are going to talk about the first point, that is the atomic size. Atomic size, right? So what do you know about the atomic size or the atomic radii? As we go down, what do we observe? The number of shells are increasing, isn't it? Therefore, we say that the atomic size increases as we go down the group, right? So, down the group, atomic radii increases. Across the period, what happens? Across the period, since the number of shell remains the same, but the nuclear charge is increasing, so the atomic pull is increasing, or the nuclear pull increases, and therefore atomic size decreases, isn't it? Atomic radii decreases. This point is clear, atomic size is clear. Next we talk about ionization enthalpy, right? So now we are going to see the ionization enthalpy down the group. How does it vary, or what is the irregularity over here? So you will see that decrease in ionization enthalpy from silicon to germanium is comparatively less due to the perfect shielding of what? The d orbitals. Clear? This point is clear? Now look at the ionization enthalpy of lead. It is slightly higher than tin. Why so? Because the imperfect shielding of the intervening f orbital. Followed? So what are we going to study over here? That the values of ionization enthalpy decrease down the group, but not in regular order. I hope this point is clear. Next we are going to talk about the metallic and the non-metallic character. Okay, so non-metallic and metallic character. So what do we know about the metallic character? It increases down the group. Why so? Because the number of shells are increasing, right? So carbon and silicon, they are distinctly non-metals, even though electrical properties of silicon are like those of the metalloids, right? But still. Now then germanium, it is a metalloid, while your tin and lead, they are typical metals. What did I say? The metallic character is going to increase down the group. How? Carbon and silicon, they are non-metals, though silicon, some of its property resembles the metalloids. This germanium is a metalloid. Then comes your tin and lead, which are metallic in nature, right? So this trend is why? Due to increased atomic radii, or in other words we can say it is due to the reduced effective nuclear charge and due to increased number of orbitals, with the size of the atom also increasing as we go down the group. Clear? So non-metallic and metallic characters also clear. We can write on over here, metallic character increases down the group. Now remember, when you are asked to explain, this is not the only thing that you are supposed to write. You are supposed to write down with explanation what I am explaining you. So if I say what happens to the metallic or non-metallic character in the 14 elements, you are simply not going to write that it increases down the group. You have to mention the reason why this happens. I hope till here it's very clear. Then we come to the fourth point, that is the melting point and the boiling point. Okay. So carbon and silicon, they have very high melting and boiling points. Okay. Carbon and silicon, they have high melting point and boiling point. Right. The values, they generally decrease from carbon to lead. Why? Due to increase in the attractive forces because of the increased size, right? So very high melting and boiling points of carbon and silicon because they form giant molecules, right? Then we come to tin and lead. What do we know about them? They have low melting and boiling points. Okay. So tin and lead, they have low melting and boiling points. So what reason did I give you? Why do carbon and carbon and silicon, they have high melting point, and tin and lead, they have low melting point? The reason is because there is decrease in the attractive forces because of the increased size, or you may say the nuclear pull is decreasing as we go down, and therefore the atomic size is increasing, and therefore they have low melting and boiling point. Whereas carbon and silicon, they form giant molecules, they have high melting and boiling points, right? Next we talk about, this was the fourth point. Now the fifth point, density. Density, except carbon, the density increases down the group. Okay. So except carbon, density increases down the group. Point clear? Now I'm coming over here, right? Coming to the sixth point, we will talk about electronegativity now. Electronegativity. So carbon, it is most electronegative element of this particular group, right? Most electronegative is carbon, right? The value remains almost same in all the other elements due to the filling of the d orbitals in germanium and tin and f orbital in the lead. Followed? So this was about your electronegativity. Now going to talk about oxidation states. Oxidation states. Okay. So this group 14, they show +4 and +2 oxidation states. These are the two states, oxidation states, that we observe in this particular group, right? Now in +4, the compounds, they show covalent nature, right? +4, they show covalent nature, whereas +2 compounds, they have ionic nature. Is this point clear? +4 oxidation state compounds, they show covalent nature, and +2 oxidation state compounds, they show ionic nature. In the +4 state, the compounds are covalent. Why? Because your C4 ion formation is energetically unfavorable. Why? Because very high energy is needed to add 4 electrons over here, right? Like for example, Be2C. What is this? Beryllium carbide, or preferably in aluminium carbide also. Okay. So over here, this compound this element carbon, it shows +4 oxidation state, and here what nature does it show? Covalent nature. Why so? Because over here carbon, it needs very high energy to add 4 electrons. Fine. Now let's talk about C4 plus ion. This formation is energetically unfavorable. Why? Because very high energy now is required to remove 4 electrons from here, right? Now compounds in +2 state, they are, what did I tell you? Ionic in nature, right? So down the group, tendency to exhibit +4 state decreases. Why? Due to inert pair effect, right? +4 state is more important in carbon and silicon. So carbon and silicon, generally they show +4 oxidation state. Germanium, tin and lead, they exhibit +2 and +4 oxidation states, right? The stability of +2 and +4 oxidation state you can understand like this. Like firstly I'll show you +2 and then I'll show you +4 oxidation state. So lead ion more stable than Sn2 plus, and least will be for germanium 2 plus. And let's look for +4 oxidation state. Over here germanium will be more stable than tin, than lead ion. Clear? So the compounds of germanium 2 plus, they are quite unstable and therefore they get oxidized to germanium 4 plus compounds easily by losing 2 electrons, right? So germanium 2 plus compounds, they are strong reducing agents. Okay, they are strong reducing agents. This point is clear. Now let me talk about Sn2 plus. They are also less stable than Sn4 plus. Why so? Now I am comparing the oxidation states of the respective elements, right? So Sn2 plus is less stable than Sn4 plus compounds, and hence they get oxidized to +4 compounds. We can also say that Sn2 is also your good reducing agent, right? Now let's compare Pb4 plus and Pb2 plus. So Pb4 plus compounds, they are less stable. See, they are less stable than Pb2 plus compounds. They are more stable. This is least stable compound. Thus, what happens? They get reduced to Pb4 plus gets reduced to Pb plus 2, right? And therefore, we can say that Pb4 plus, they are powerful oxidizing agents. They are powerful oxidizing agents, right? I hope till here it's very clear to you. Now, some more points to be explained. I'll just rub this much part and then explain it to you. Now, since SnCl2, it is less stable than PbCl2, isn't it? So, it is a better reducing agent than PbCl2. Who is better reducing agent? SnCl2, it is a better reducing agent than PbCl2. Why so? Because PbCl2 is less stable than Pb2 plus. Clear? On the other hand, let's see. So let me write it down over here. This is your reducing agent. It is a better reducing agent than PbCl2. Now, let me compare between PbCl4 and SnCl4. So over here you will see that PbCl4, it is less stable than your SnCl4, isn't it? So it is a better oxidizing agent than your SnCl4. So this is your better oxidizing agent than SnCl4. So these are certain questions which could be asked to you in the form of arrange the following according to the increasing reducing agents or decreasing oxidizing agents. So this is what you need to remember, and then it will be easy for you to explain. Clear? So over here, if we talk about the different types of compounds, according to Fazan rule, you already know that smaller the cation, greater is the covalent character of its compounds. So SN4 plus compounds, they are covalent. Why? Due to smaller size of the SN4 ions, and SN2 ions, they are ionic. Why? Due to larger size of this ion. Clear? So in general, what did we study? That +4 state they are all covalent in nature, and +2 they are all ionic in nature. So I hope oxidation state is also very clear to you. We next move to catenation. The catenation power. What is catenation? I hope you all know what is catenation. The ability of the like atoms to form covalent bonds with another atom, that is called as catenation. Catenation power decreases in moving down the group, right? So what are the necessary you may say conditions for catenation? Firstly, the valency of the element must be greater than or equal to 2. That is important. Secondly, the element must form strong covalent bonds between the two atoms as compared to the bond with another atom, especially with the oxygen, right? So these are the two important conditions necessary for catenation. I repeat, what are the two important conditions for catenation? Firstly, the valency of element must be greater than or equal to 2. This is the first point. Second point necessary for catenation is that the element must form strong covalent bond between the two atoms as compared to the bond with another atom, say if we talk about oxygen. So over here we will see that the catenation, more of the catenation can be observed in carbon, and as we go down the group, the catenation decreases, right? Now let's talk about catenation in carbon. It is observed that carbon atom shows catenation. Why? Because it is a tetravalent element, right? And over here, the carbon-carbon bond energy, it is around 353 kilojoules per mole, right? And this bond energy is somewhat of the same order if we see between carbon and oxygen. The bond energy is say 351 kilojoules per mole. So you can see there is not much energy difference over here. So carbon atom, due to its tetravalency, can be bonded to 2 or 3 or 4 carbon atoms by either a single bond or a double bond or a triple bond, and it can also form a long chain, a straight chain, a branched or a cyclic bond can be shown by them, right? Catenation is not shown by other elements. Why so? Let's talk about silicon. Why to go till this tin and lead? Let me talk about silicon and tell you. In silicon, the bond energy is 226 kilojoules per mole, right? But if we see the bond energy between silicon and oxygen, it is 368 kilojoules per mole. So you can see there is much difference in the bond energy of the two, and therefore they are unable to show the catenation. I hope this point is clear. Then next we are going to talk about allotropy. I hope you know what is allotropy. it is a property by virtue of which an element may exist in two or more forms which have different physical properties but almost similar chemical properties. No, you have already studied about this earlier. I repeat, what is allotropy? It is the property by virtue of which an element may exist in two or more forms which have different physical properties but almost similar chemical properties. So all the elements except lead over here, all elements except lead, they show allotropy. Is that clear? So let's talk about carbon firstly. You all already know it exists as a diamond, as a graphite, in coal, coke, the different charcoals like animal charcoal, sugar charcoal, bone charcoal, lamp black, gas carbon, and petroleum coke, and so on. So these are the different forms of carbon. Then germanium also, it exists in two allotropic forms, right? Whereas tin, it is found in three allotropic forms. The white tin, the grey tin, and the rhombic tin, right? So this was about allotropy. So with this we wind up with the physical properties of group 14 elements, right? In the next video I shall come up with the chemical properties and certain trends of group 14 elements. Thank you.